Good morning, learners. My name is Mr. Pochilola once again. Let me welcome you to Black Slides online platform. This is the only place where you learn Msce science subjects at no fee. And at no point will you be required to pay a fee for these lessons. I welcome you to the topic of the day, which is called electromagnetic spectrum. It's a Form 4 topic. It's a Form 4 topic, Msce Form 4 Physics. In case you have queries, questions, comments to make, don't hesitate to reach me on the number shown on this screen. And in case you have comments to make, don't hesitate again to contact me directly on this number, or you can make a comment. You can just comment in the comment section on this forum, on this YouTube channel. Once again, my name is Mr. Pochilola. In this topic, we are going to focus on the following objectives. So by the end of this topic, you should be able to describe the complete electromagnetic spectrum. So we are going to look at what the electromagnetic spectrum is and what it is composed of. What is it made up of? Right? You are going to learn that the electromagnetic spectrum is made up of electromagnetic waves. So what are the properties of electromagnetic waves? All right, so by the end of the topic, it's one of the shortest topics in Form 4 Physics. You should be able to describe the complete electromagnetic spectrum, state the properties of the components of the spectrum, which are called electromagnetic waves, describe the methods of detecting electromagnetic radiations, where it is present, where the electromagnetic radiations are present, how can you detect their presence? So discuss that. And last but not least, you are also expected to use what is called the wave equation. The wave equation. From your Form 3 physics, when you were looking at mechanical waves such as sound, waves in a spring, water waves, and other waves, you met the wave equation given by V equal to F multiplied by lambda. Okay, that's the speed of a wave is equal to its frequency multiplied by its wavelength. All right, so you're familiar with this one. So with respect to the electromagnetic waves, we don't use a V for speed, we use C. C is the general term for speed, the general symbol for speed of electromagnetic waves, including speed of light. So we are saying the speed of light, speed of X-rays, speed of gamma rays, radio waves, is characterized by, or is given by, the frequency multiplied by wavelength. Remember that wavelength is represented by the symbol, the Greek symbol lambda. So these are the areas that we are going to focus on. Specifically, we are going to look at the electromagnetic spectrum, as I said. So the electromagnetic spectrum is made up of what are called electromagnetic waves. So we'll talk about their properties. Then we'll discuss how electromagnetic waves can be detected. There are different methods of detecting electromagnetic waves or radiations. So we'll discuss them. Later on, we are going to look at the practical applications of electromagnetic waves. Electromagnetic, in short, is EM. E for electro, and M is magnetic. So EM radiations is the same as electromagnetic radiations. So we are going to look at their applications in everyday life, including what we call the greenhouse effect. And then lastly, as I mentioned, you're going to look at how you can apply the equation speed of light or speed of electromagnetic waves equal to the wavelength. Wavelength is the lambda multiplied by frequency. And also apply your knowledge of mathematics, change of subject or formula to solve for any of these when enough information is given. So wavelength can be expressed as speed divided by frequency, and therefore frequency can be found by simply dividing speed by wavelength. So we are going to look at these equations and how we can use them to solve problems. Once again, my name is Mr. Pochilora. I teach physics here, and I also teach physics at a physical school in one high school in Blantyre. All right, so welcome once again. I believe you are set. You have your notebook ready, your pens, pencils, calculators where they're needed, and you have also enough water by your side. Remember, I mentioned that in order to focus very well, you must be well hydrated. So you must drink enough water to stay active throughout this lesson. Right. So let's look at the electromagnetic spectrum in terms of what it is. We define the electromagnetic spectrum. The electromagnetic spectrum is defined as the arrangement. So a spectrum means a number of things put together, okay, arranged according to some order. All right, so it is the arrangement of electromagnetic waves according to their frequencies or according to their wavelengths. All right, from your Form 3 physics, you do recall what frequency is. Frequency is simply the number of complete cycles made per second or per unit time, but the time there is in seconds. So the number of complete cycles or complete oscillations per second is called frequency. So these electromagnetic waves have different frequencies. So when you arrange them according to their frequencies, whether in increasing order or decreasing order, you make what is called electromagnetic spectrum. You can also arrange them. They can be arranged in order of increasing or decreasing wavelength. Remember, wavelength is simply the distance between any two successive identical points of a wave. It can be the distance from one crest to the next one, or from one trough to the next one. So that's called the wavelength. Okay, measured in meters. Okay, so we are saying that the electromagnetic spectrum is simply that group of electromagnetic waves which are arranged according to their increasing frequencies or decreasing frequencies, or increasing wavelengths or decreasing wavelengths. Any of these two criteria can be used to come up with the electromagnetic spectrum. So what are electromagnetic waves? We define electromagnetic waves as transverse waves which result from oscillating electric and magnetic fields. So when electric fields and magnetic fields interact at a 90-degree angle to each other, they are going to generate electromagnetic waves. I hope you get that. So for an electromagnetic wave to exist, there must be two things. One, there must be an oscillation of electric and magnetic fields at right angles. Two quantities must interact: electric field and magnetic field. Their interaction should take place at a 90-degree angle or right angle. So the result is called the electromagnetic waves. So take note that they are transverse in nature. They are not longitudinal like sound waves, no. So as transverse waves, it means they are characterized by troughs and crests. So they have crest, trough, and trough, like that. These are called this wave function is used to represent an electromagnetic wave. Remember, the opposite of electromagnetic waves is mechanical waves. Mechanical waves examples are sound, water waves, seismic waves, waves in a spring, and others. All right. So what are electromagnetic waves? We are saying they are transverse waves which result from oscillating electric and magnetic fields at right angles to each other. Take note of these definitions. They are very, very important. So some examples of electromagnetic waves include, but not limited to, X-rays, UV radiation, or what is called the ultraviolet radiation, infrared radiation, gamma rays, and others. So these, when arranged in terms of wavelength or frequency, they form an electromagnetic spectrum. Electromagnetic spectrum. So I hope you are good on that. So we have defined electromagnetic spectrum as the arrangement. So you have the arrangement of electromagnetic waves based on their increasing frequencies or wavelength. All right. So this diagram here is used to represent the electromagnetic spectrum the electromagnetic spectrum. We have two criteria only, or criteria, that are used to arrange these waves, these electromagnetic waves. So what we call electromagnetic waves here, we have 7 of them. We have radio waves, microwaves, infrared waves, visible light. Visible light is the light that you see, that we receive from the sun, or that you receive from fluorescent tubes or incandescent tubes, the light bulbs in your house. The energy saver bulbs give you visible light. But also we have UV radiation, X-rays, and gamma. So 7, take note, there are 7 of them. However, if you look at the radio waves can be AM, or amplitude modulation, FM, frequency modulation, or TV for television, as well as what is called radar. So, or radar, some pronounce this as radar. So radio waves can be FM, AM. AM is amplitude modulation. You hear on the NBC Radio 1 that you are tuned to NBC Radio 1, and you can hear us on its frequency of, so they mention numbers, 96 point what, FM, okay, FM. But before frequency modulation came into being, the FM technology came, they were using amplitude modulation. If you take radio technology after school or in college, you're going to learn about these things in detail. So what I'm saying is, under radio alone you have amplitude modulation, FM, TV, and radar. You don't show these in the spectrum here. So you just say radio. But inside the radio we have these 4. Alright. So the first one, based on size of wavelength, the highest is that of radio wave. Okay, so we're saying radio waves have the larger magnitude of amplitude, and the gamma rays have the least. Okay, so we are talking about radio waves having the highest wavelength of 10 to the power 3, and the gamma rays having the least of 10 to the power minus 12. It's very, very small number. Okay, you can see here that 10 to the power 3 is actually the same as what? 1000, right? This is 1000 amplitude. These are 1000 meters. 1000 meters, the distance between any two crests, adjacent crests, 1000 meters. You can see here, this is larger. So we are talking about this distance. It's very, very high, 1000 meters. But if you look at that of gamma, gamma is 10 to the power minus 12. 10 to the power minus 12 is a very small number. It's 0. You have 11 zeros and a 1. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is very, very small number. It's very small number. So we are saying the wavelength of gamma waves is very small. It's actually the minimum in this spectrum. Is the minimum, while radio, for radio, is the maximum, and all others come in between. So you can see what order this is. This is a descending order. This is a descending order. As you move from radio waves to gamma rays, the wavelength is decreasing. It's decreasing. Okay. Another criteria for this, for arranging them, is using frequency. Using frequency. So when the frequency is used instead of wavelength, you can see that frequency increases. Back to this, wavelength decreases as you move from radio to gamma. There's an increase, okay? But as you move from radio to gamma frequency, what is happening? Frequency is increasing. Wavelength decreases. Frequency increases. From gamma, from radio to gamma. So compare, look at this is 10 to the power 4, that's 10,000. 10 to the power 4 is 10,000 hertz. But as you move from radio, going all the way to gamma, we are comparing these values here. You find that it's 10 to the power 20. 10 to the power 20 is 1 times with 20 zeros in front of it. That's a lot of frequency, high frequency. So this for radio, the frequency is more minimum. Okay, minimum. Well, the frequency is mini. For the frequency is mean for what? For radio waves, and max for gamma rays. You can see there that 20. This is 10 to the power 4, 10 to the power 8, 10 to the power 12, 10 to the power 15, 10 to the power 16, 10 to the power 18, 10 to the power 20. So the numbers are increasing. So from frequency, from radio to gamma, the frequency is increasing, but the wavelength is decreasing all across. Okay, that's very, very important to note. Right, unless you have questions, let's proceed. Let's proceed. So what we said is that the one important criteria is to arrange the radiations, the waves, in order of increasing, decreasing wavelength from radio to gamma, or in order of increasing frequency. Now this chart here is giving us another criterion to arrange the electromagnetic waves in the spectrum. That's using their energy, right? So as you move from gamma radio, so this is radio. Up here you have its wavelength. So we said the wavelength is 10 to the power 3 meters. This distance here is 10 to the power 3, or 1000. Right? So as you go to the left, the distance between any successive crest is decreasing. So the wavelength is decreasing from right to left, from gamma to microwaves to infrared to visible light. There is a decrease. You can see this is decreasing. This is 10 to the power 6 nanometers. Nano means 10 to the power minus 9 meters, very small. So there's a decrease going this way. Take note, we are starting with radio from this end. So going this way, wavelength is decreasing. Remember, wavelength refers to these distances, the distance between this crest and this one. That's wavelength. So compare it with this distance. It is bigger here than it is this one here, and it keeps on decreasing as you move further left. So what I want you to look at, to consider, is that as we are moving from radio waves, which has greater wavelengths, to far left, let's say to gamma rays, there is an increase in energy. So gamma rays have more energy than the X-rays and the rest of the radiations, which are to the right. All right. So as you move from radio waves to gamma rays, energy tends to increase. Okay. So they may ask you in an exam to arrange. They can just mix up the radiations, and they ask you to arrange them in order of increasing energy. So you have to know this order. I will tell you how you can remember the order very easily. So we are saying, apart from using wavelength and frequency, we can use what? Energies. So the longer, you can see here, the longer the wavelength, the smaller the the energy. So energy increases as frequency, as wavelength decreases. Okay. So you can arrange them. When given a situation, you should be able to arrange them in that particular order, whether increasing or decreasing order. Right. Next, let's look at their properties. What are the properties of electromagnetic waves? Alright, so these properties, before we proceed, are common to all electromagnetic waves. So they can ask you in an exam to state any two properties of electromagnetic waves which are common to all electromagnetic waves. So in this case, you can mention any one of these. So one of the properties we are saying is that they are transverse in nature, meaning when they are being propagated, they form a wave function like this. Okay, they form a wave function like this with crests and troughs. So they are transverse troughs. So they are transverse in nature. They are transverse in nature. So they are characterized by crests, troughs, and so on. They are different from another type of waves which is called the longitudinal. Remember, longitudinal waves are characterized by rarefactions and the compressions. So rarefactions and we are saying longitudinal waves, how they differ from what? From transverse waves is that longitudinal waves have rarefactions and compressions. Remember, rarefactions are regions of lower density of particles that are involved in the transmission of energy, in this case sound energy, and compressions are regions of higher density. So we are saying that transverse waves, rather electromagnetic waves, do not behave like this. Okay, they don't behave like that. They behave like this. So they have crests and the troughs. That's what we mean by being transverse. So all of them. An example is light. For example, light is a transverse wave. Light is transverse wave. All right. The second property is that they do not require medium for transmission, meaning they don't require matter. Medium here refers to matter. So they can be propagated without matter. Matter, for example, can be liquid, can be gas, or can be solid. Right, so they don't need or they don't require matter to travel through. All right, in that same regard, they are said to travel through space. Space is what is called the vacuum. Vacuum, remember, vacuum is completely empty space at a speed of 3 times 10 to the power 8 meters per second. This is very high speed. It is the same as 300 million meters per second. Very big speed, very high speed. Okay, very high speed. So we are saying all electromagnetic waves travel at 3 times 10, speed of 3 times 10 to the power 8 Right. Apart from that, they also are said to travel or to carry no charge. So they are not charged. And therefore they may not be affected by electric or magnetic fields. All right. So what this means is that because of their lack of charge, if you have a field, let's say you have a south pole of a magnet and another pole of a magnet, say north, and you let the radiation pass through, it will not turn to either the south pole or the north pole. It will just pass through in a straight line. Okay, why? Because of no charge. Only charged particles can be affected by an electric field or magnetic field. Right. Other than that, they can undergo interference. They can be refracted, they can be refracted, diffracted, or refracted. Okay, so they undergo interference. Let's say that you have one of them traveling like that and another one traveling like this. Okay, these two can interfere with each other by cancelling each other out. Okay, so that there is no amplitude, there is no wave, or they can reinforce each other. This is called the destructive interference, as you learned in Form 3. Or you can have one traveling in the same phase, in the same direction as the other one, like that. The result is going to be a build-up of a wave which has greater wavelength. So just review your notes on these behaviors or properties of waves. Right? They can also be refracted if they meet a barrier. Let's say that a wave is traveling like that. The wave is traveling like that, in that direction, and upon reaching a barrier, they can go a different way. We call this bouncing. So they can refract. So this is incident, this is refracted. All right, so this is called the refraction. Or they can be diffracted, meaning that they can pass through gaps. So let's suppose we have a slit or gap, and then you have this wave, which is electromagnetic, traveling all the way. Upon coming out of this gap, the slit, they're going to curve out like that. Okay, usually it's because of their increase in pressure, the increase in pressure between the two objects. So the increase in pressure will cause them to bend. So this bending after passing through the gap here is what is called the diffraction. Also, they can be refracted, when they pass through two different media, or media of different optical densities. Let's say that they are traveling from one media through maybe air, and then upon reaching this surface here, they bend. So they can bend, and they find that they change their direction of travel. So that is called refraction. Like that, just go and revise your notes. These things are clearly stated, explained in the notes. They also possess different amounts of energy, which can be calculated using this equation. This equation is saying that the energy possessed by a wave is given by, or found by, multiplying the Planck's constant by frequency. This should be Planck, not planets. Planck's constant, okay, of this magnitude. So multiply the frequency and the Planck's constant, you get energy of the wave. Other than that, they all obey the equation, which is called the wave equation, where C here is speed of the wave, and the F is frequency. Okay, frequency, while lambda is the wavelength. So we are saying the speed of these electromagnetic waves is found by multiplying their frequency. If you know the frequency and you know the wavelength, you can simply multiply the two and find what you don't know. Be able also to make the other variables subjects of the formula. For example, frequency will be speed divided by wavelength. All right, I hope there we are good. So these are the properties. They are also characteristics, basically. Now let's look at their production, detection, their production and detection. All right. So in this column we have the electromagnetic waves. So radio waves, microwaves, infrared, visible light, and others in the next slide. All right. So radio waves are basically produced by oscillating electric circuits and transmitted through areas or antennas. For example, if you have a radio at home, for you to receive the radio signal, it has an antenna or an area. So you protrude the area into the air, your radio system is going to receive signals, and you hear a live broadcast at that particular moment. So in order to detect radio waves, all you need is simply a series of diodes and the earphones or headphones. Nowadays you have headphones that are made of Bluetooth, and that have Bluetooth, and or those that have strings. Whichever headphones or earphones you use, they will be able to detect the presence of radio waves. Microwaves are produced by special vacuum tubes, which are called magnetrons in microwave ovens, or with the Msce. Microwave oven is a device, it's a home appliance that is used for cooking, for warming foods and other stuff. All right. Okay, so how are they detected? These can be detected by dry crystal detectors, or what we call solid state diodes. You find solid state diodes in cell phones, because microwaves can also be used for communications, like cell phones, using cell phones. Okay. Then we have infrared, known as the IR. These are produced by the sun or any hot object, As a matter of fact, IR or infrared is a technical word for heat. So when you are basking in the sun, the heat that you receive from the sun is called infrared. Or when you are sitting close to a charcoal burner, such as Mbaula for example, you feel hot. That heat which you receive from there is called the infrared. Okay, so the sun produces that kind of energy. So heating effect produced, you can tell that there is heat by simply feeling the heating effect produced on your skin, okay, but also by using what are called the thermopiles, bolometers, and the thermometers with a blackened bulb. So these can detect the heat. Example, when you dip a thermometer in a hot substance, you see the temperature rising. So that is one way of detecting infrared radiation. Another one is visible light. Visible light comes from the sun. The sun is the main source, apart from hot objects, lamps, and laser beams. Okay, so during the daytime, you receive light from the sun. And that light is the one which enables us to see things. It enables us to see each other, to appreciate the world around us, and all that. When it is night, that light is gone, and you can no longer see light. So they may ask you in an exam, state the source of visible light. So visible light is produced by the sun, but it is also produced by lamps in your house, bulbs, fluorescent tubes, laser beams. These are special beams which also produce visible light. The eye can detect visible light. That's why you say there is light when you see one. All right, that's when you turn on lights in your house, your eyes will see the light. So eyes in that case are detectors of visible light. But also photographic films. Photographic films are coated with some chemicals such as silver bromide. When you expose photographic film to light, the film will change its color due to the reaction that happens between the visible light and the chemicals that are coated on the photographic film. But also photocells, which are used for making solar panels, those also react with light, can detect light through a process known as photoelectric effect. Okay, so please, what you need to know for the good of your exams, you need to know the type of radiation, how it's produced, and how it can be detected. All right, UV radiation. UV radiation, or ultraviolet rays, are also produced by the sun. Sparks, mercury vapor, due to large energy changes. This should be changes, not chances. Changes in the electrons of an atom. These can be detected by photographic films, photocells in solar panels, fluorescent materials. An example is quinine sulfate, and the paper lightly smeared with Vaseline. When you take paper, smear it with Vaseline or cooking oil and hold it against light, you see a translucent spot there. Okay, that translucent spot is used to detect light. I mean UV radiation. Okay. X-rays produced by the action of beam of fast-moving electrons hitting a metal target. This should be hitting a metal target. So in order to detect them, use the fluorescent screen or photographic film. Please, for each radiation, know how it is produced and how it can be detected. Then you have gamma rays. Gamma rays are produced by radioactive substances. It's one of the radioactive radiations. apart from gamma, apart from beta and alpha, gamma is another one. Notice that gamma rays are rays, they are not particles. So these are produced by radioactive substances in the nucleus of an atom. They can be detected by photographic plates and the radiation detectors. An example is the GM cube, which you are going to discuss in a topic called radioactivity. For now, I would like to leave you here. So we've looked at the electromagnetic spectra, electromagnetic waves and their properties, and then production and detection of electromagnetic waves. So when we meet next time, we are going to look at the applications of electromagnetic waves. So far, I would like to stop here. Thank you very much for being there. Notice that this is a free class. You can tell your friends to come, as many as possible. Tell them to come. Tell them to clamber here, to gather here and learn for free. No fees needed. Okay? So just, bring your materials, your book, your notebooks, your pencils, pens, and the others. So for me, my name is Mr. Pochilola once again. I love to teach you. I love to be here. All the best as you study, as you prepare for your 2025 Msce exams. I want you to pass and pass very well. All right. So thank you very much once again. Bye for now.